Hey everyone, and welcome to this WACE Academy lesson on collision theory. We'll be covering points 1, 2, and 4 in the chemistry syllabus of the subtopic Chemical Equilibrium Systems. To start this lesson off, we'll begin with collision theory before moving on to the factors that affect the rate of a chemical reaction. Then we'll move on to reversible reactions and the theory of chemical equilibrium. Finally, we'll end with the different types of chemical systems. So, collision theory states that in order for a chemical reaction to occur between two gas particles, the particles must first collide together with enough kinetic energy to begin the reaction. This minimum kinetic energy that we need to kickstart the reaction is called the activation energy, and changes depending on the reactants involved in the reaction. We can imagine this idea as pushing a rock up a hill. As we keep pushing, eventually it'll reach the peak and begin to roll by itself down the other side of the hill. With this analogy, the energy that we use to reach the peak of the hill is the activation energy. That being said, not all reactions occur at the same rate. Some reactions occur faster than others. An example of that would be rusting iron versus an explosion. Reactions in an explosion happen at a much higher rate than that in rusting iron. Let's now take a look at the specific factors that can affect this rate of reaction, or how quickly our boulder rolls down the other side of the hill. So, there are several factors that affect the rate of chemical reactions. These include concentration, pressure, temperature, surface area of reactants, and catalysts. Let's start with concentration. If one solution has a higher concentration than the other, that means there are more particles in the same volume. If there are more particles, it makes sense that they would collide more frequently. That will then lead to the reaction going faster. So a higher concentration equals a faster rate of reaction. Next up is pressure. Now with pressure, we're only talking about gaseous reactions, because generally you can't increase the pressure of a liquid or a solid. So with gases, the increase of pressure increases the rate of reaction, and the reason for this is because it has the same effect as decreasing the volume, which effectively increases the concentration. As we already know, an increase in concentration causes an increase in collisions and subsequent rate of reaction. An increase in temperature also increases the rate of reaction. This is because increasing the temperature gives the particles more energy. That way, more of the particles reach their activation energy, and because they're moving around faster, there's more chance of a collision occurring, which is essential to begin the reaction. An example of this would be dissolving a cube of sugar in a cold glass of water compared to in a hot glass of water. You would notice that the cube in the hot cup of water dissolves way faster than that in the cold cup of water. So increasing the temperature increases the rate of reaction. The last factor we'll look at is the surface area of the reactant. Increasing the surface area will increase the rate of reaction, as more particles are exposed to the other reactant. Let's go back to the sugar and water example. Assuming both cups have the same temperature of water, now add one cube to one cup, then crush another cube of sugar and add it to the other cup. You'll notice that the crushed sugar will dissolve faster than the sugar cube, as it has more surface area exposed to the water. All of the crushed sugar is in contact with the water, while the middle of the sugar cube will not be. I know these various factors can be quite overwhelming to take in at first, so we'll summarize them in a table. A trick I used, which I think is really essential for this part of the syllabus, is to understand why each factor causes its effect. I know you've probably heard this a lot, but it's really quite simple here, and I promise once you can get it, you won't forget it. Now, assuming all the other factors mentioned above cannot be changed, catalysts can also be used to increase the rate of reaction. But what are catalysts? Catalysts are any substance that increases the rate of a reaction without being consumed or used up in the reaction itself. The reason for this is that they provide an alternative route for the reaction to occur by that has a lower activation energy. Imagine adding a shortcut to the city from the freeway. A lot more cars would get to the city faster and effectively increase the speed the cars are traveling. Some chemical reactions are reversible reactions, meaning there are both forward reactions in which the reactants form products, and then backward reactions where the products can form reactants. In other words, the reaction is constantly going back and forth. We can write the general form of this as A and B react to form C and D, and also C and D react to form A and B. The double arrow in the middle indicates a reversible reaction. Chemical reactions can reach a point which we call dynamic equilibrium. This is essentially when the forward and backward reactions level out and reach a balance. Dynamic equilibrium is reached when the rate of the forward reaction is equal to the rate of the backward reaction. In other words, the rate at which C and D is produced is equal to the rate at which A and B is produced. If the concentration of the reactants increases, the forward reaction will be favored. However, if the concentration of products increases, the backward reaction will be favored, and the rate of the reaction increases in that direction. A good analogy for this concept is a child walking up an escalator that is traveling downwards. The child will reach a balance or equilibrium when they walk the same speed up the escalator as the escalator is traveling down. They'll stay in the same spot, but if they walk too slow or too fast, they'll move from this position and be out of balance. For a reaction to reach dynamic equilibrium, it must be in a closed system where there's no exchange of matter with the outside surroundings. Energy, on the other hand, is able to enter and leave the system freely. So closed systems don't allow matter to enter or exit a system, only energy. But what about one that does allow matter to leave or enter freely? This is called an open system. Creative name, right? In an open system, which is the opposite of a closed system, we can no longer achieve equilibrium since some of the reactants and products will escape and no longer react with each other. Hence, no balance between forward and backward reactions. Alright, that's all for our lesson today. It was quite a lot to take in at once, but overall this content is quite straightforward, and again, if you can understand the simple reasons behind each concept, you should be all good with remembering them later. I hope you enjoyed this lesson, and I'll see you next time.